The whole next page is just about solving equations. So there's a variety of strategies we're going to have to use. This one, you might remember, is called the zero product property. We want to know when each term is zero, because all of the terms are multiplied together. And when I have any number of things multiplied together, if the solution is zero, that means one of them had to be zero. Doesn't matter which one, which is why we get 4 separate solutions here. So I'm going to take each term. Negative 5x equals 0. 2x plus 3 equals 0. X minus 12 equals 0. And x plus 1 equals 0. And then each of these I just solve using algebra steps. Divide by negative 5. X equals 0. Minus 3. 2x equals negative 3. Then I have to divide by 2. Negative 3 over 2. Or negative 1.5. Same thing. Then I add 12. X equals 12. That one was quick. Then minus 1, minus 1. X equals negative 1. That one was quick as well. So I get 4 solutions, one for each of the terms that was multiplied together, one of each of the factors. So zero product property, pretty simple to apply. It works best when something's already factored like this. This one is kind of a masked factoring problem, so we'll use it as another quick factoring review. To be able to solve this, I'm going to want everything on one side. So I'm going to add the 11w over. Had a negative, a positive will cancel it out. 5w squared plus 11w plus 2 equals 0. I purposefully wrote it with the 11w in the middle because it's our b value. So now I'm going to do my whole factoring process. So I'm going to start by doing a times c. 5 times 2 equals 10. And then I'm going to factor 10. I'm looking for things that add to 11. My options are 1 and 10, 2 and 5. 1 and 10 is the pair that adds to 11. So now I'm going to do my little number puzzle thing. 5w squared and 2 go in the diagonals here. And then these numbers, 1 and 10, make 1w and 10w in the other diagonal. So we'll start with the simple stuff. What can go into 1w and 2? Well, the only number that can go into 1 is 1. And then 1 times something gets me 2. 1 times 2. 2 times something gets me 10w. That's got to be 5w. And 1 times something gets me 1w. That's just got to be w. So these are my factors. So now this is w plus 2 and 5w plus 1 equals 0. And now we're back to the zero product property. W plus 2 equals 0 and 5w plus 1 equals 0. I got it to factored form, but you can't stop here because those aren't actually the solutions. Those are the factors, not the solutions. So I got to do my algebra steps again to finish off this problem. Divide by 5. I get negative 1/5 for this one. So you can go back and plug these in, but they should be right. Now, if I do negative 1/5 here, let's see, that's going to be 1 over 25 when I square it. 5 over 25 is just 1/5. 1/5 plus 2 is 2 into 5th. Negative 11 times negative 1/5 is positive 11/5. That's also 2 into 5th. So yeah, we can always plug these back in. You shouldn't get anything too crazy when you're factoring. As long as you were finding things that worked every step of the way, that's a good sign you were doing it right. Not all of them are going to be able to be done by factoring, like the next handful we're going to do with the quadratic formula. You can also do this one with the quadratic formula. In fact, it makes a lot of sense to if you're not as confident with your factoring skills. This one, factoring in the quadratic formula, don't make a whole lot of sense for because I have no b value. Just solve. When you have no b value, you can just use your normal algebra steps. So I'm going to start by trying to get the x squared alone. So I'm going to subtract the 40 over. Negative 4x squared equals negative 40. And then I got to divide by negative 4 to get x squared alone. X squared equals 10. All right. I'm going to square root that. And I get x equals 10, square root of 10, and x equals negative square root of 10. It's going to be 3 point something, like 3.2 or whatever, 3.1, 3.2. But I would accept this on the actual test. It's not a perfect square, so I didn't tell you to estimate. This would be perfectly fine. If we did the quadratic formula, we should get exactly the same thing doing this. So here's another one that would be really good to factor on if you realized you could do it. I'm going to add 5 to both sides because we need to for the quadratic formula anyway if we were going to use that. So no matter what method you choose, adding 5 over is the best first thing to do. All right. So factoring time, a times c, 1 times 5 is 5. Find factors that add to negative 6. Now remember, I can use 1 and 5, but I can also use negative 1 and negative 5 because a negative times a negative is a positive. So those are my factors. Fill out my little table here, my number puzzle. I have x squared and I have 5. And then these fill in the other diagonals, negative 1x and negative 5x. All right. Now this is easy because x squared can only mean one thing. X and x go here and here. So x times what is negative 5x? Negative 5, that's easy. X times what is negative 1x? Negative 1, that's easy. Now let's check our last box. Negative 1 times negative 5, that is indeed positive 5. So these should be my factors. You got x minus 1 and x minus 5 equals 0, and zero product property again. Might be able to mental math this. We did that a lot during the unit for some of these simpler factors. Because if I ask you the question, x minus 1 equals 0, what's x? Most of us were able to just shout that out right away. So those are my 2 solutions for this one. Again, factoring is probably the fastest way to solve this, but quadratic formula also technically works. Now, we could try to factor this one, but we won't find something that works, which is why I'm saying if you can't tell, quadratic formula should always get you to the right answer if you're good at it. This one has to be quadratic formula. There's no other way that we've learned to solve this. You'd be crazy not to have at least one example of this on your note card to make sure you don't mess up any of the steps. But my A is negative 5, my B is negative 1, and my C is 7. So I'm going to start filling in. Negative, negative 1, plus or minus a square root, negative 1 squared. We made a lot of mistakes here during chapter 9. All right, put that in parentheses. People were getting negatives when they squared this. You should never get a negative here. B squared should always come out to a positive number because you're squaring a negative or you're squaring a positive. And A is negative 5, C is 7, all over 2 times A, so 2 times negative 5. So let's simplify some stuff. Negative, negative 1 is 1, plus or minus the square root of, let's do some of these, negative 1 squared is 1, and then negative 4 times negative 5 is 20. 20 times 7 is 141. The negatives canceled out, so it's plus here instead of minus, so I will have answers. Over 2 times negative 5 is negative 10. All right, now, because we're not going to be square rooting a perfect square, 1 plus the square root of 142 over negative 10 is an okay answer. This is an okay answer. It's an exact answer. That means we didn't get decimals because we weren't going to get clean decimals. So it's a negative 10 right there. I know it's in the glare. Then the other one is 1 minus square root of 142 over negative 10. So I'm going to pause the videos and get the decimals written down too, just so you can see them. So these are the decimals I get, negative 1.29 and 1.09. And last equation to solve. This is another one that's actually not good for factoring. We're not going to be able to find something that gets negative 12 for us. We will have solutions. They're just not going to be pretty solutions. All right. So we're going to do a equals 1, b equals negative 12, c equals negative 20, and start up with the quadratic formula again. Negative b, negative 12, plus or minus the square root, b squared, so negative 12 squared, again, putting that in parentheses, minus 4, a is 1, c is negative 20, all right, divided by 2a, so 2 times 1. Now let's start simplifying stuff. Negative 12 is just 12, plus or minus the square root of negative 12 squared is 144. Negative 4 times 1 times negative 20 is positive 80, so plus 80, then divided by 2. Once again, this isn't going to give us clean square roots, so I'm going to be fine with 12 plus square root of 224 over 2, and 12 minus square root of 224 over 2. Let me get the decimals one more time. Those should be 13.48 and negative 1.48. Again, sorry about the glare. Number 26 should be pretty straightforward. There's not really much calculating to do, just vocabulary and knowing what to look for on the graph. So axis of symmetry is our fold over line, so I'm going to put a dashed line here. This is the line it's symmetric over, hence the name. So this is at x equals 1. Axis of symmetry is always written as x equals something for a quadratic. Vertex is going to be that point where it curves back around. So that's at 1, 4. Vertex should always be written as a point in ordered pair. Domain is going to be all reals, just like it always is for a quadratic. I can plug in any x value, so I have no restrictions, so domain is all real numbers. Range is my y value, so it's going to be y greater than or equal to or less than or equal to something. This is where we have to look for a maximum or a minimum. Now ours is like a mountain where it tops off, so it has a maximum. Everything is below that point. So ours is y less than or equal to this y value, which is 4. It comes from the vertex number. And then x-intercepts, those are our solutions where we cross the x-axis. So my x-intercepts are at negative 1, 0 and 3, 0. All right, so my solutions, if I wanted to write solutions, I'd say x equals negative 1 and x equals 3. Okay, x-intercepts are points. Solutions are the actual like x equals that we were finding on the last page. But really the same idea for x-intercept and solution. These next two problems we're going to do in 2 different ways. It's graphing quadratics. So this first one, I mean, it looks a little more like standard form, but technically we could treat it like vertex. But I'll do this one with a table of values, just, you know, so that we see both ways. We're gonna want to start with the axis of symmetry. That's the equation negative b over 2a to find our x value for the axis of symmetry. So we're going to have no b value here. B equals 0. Our a value is 2, and our c value is 3. All right, so we're going to have negative 0 over 2 times 2. 0 over 4, or just 0. Okay, so we should plan on this one having an axis of symmetry down the middle. I like to draw that right away. And now I'm going to make my table. So I'm going to try and make a table of values that can hold at least 5 points. And I'm going to put 0 smack dab in the middle, because that's my axis of symmetry. And then 1 and 2, -1 and -2, just to get a nice shape of the U around the vertex. So we really only need to plug in one number as long as we're smart about what the stretch means, that A value. So the only number I really need to plug in is 0, g of 0. 2 times 0 squared plus 3. 2 times 0 is just 0. So the first point is 0, 3. All right, after that, I'm going to write down what the parent function does, just as a reference. All right, this is going to tell us how much we should increase by. Because our stretch, our A value is 2, I'm going to double all of these numbers. Okay? So our pattern should go from 0 to 2, an increase of 2. All right, but our number starts at 3, so to go up by 2, I go up to 5. This is just a strategy so we don't have to plug in so many different answers. And then to go from 2 to 8, that's plus another 6. Plus another 6 for us is going to go up to 11. 5 plus 6 is 11. So I should have given myself a little bit bigger graph here, but it's going to be a stretched U shape. There'd be another point way up that way that we could have gotten with the 11s, but I only drew my graph up to 5. This is one way of doing it, just with a table of values and finding your axis of symmetry. The next one's going to be vertex form. So should be able to do that just erasing this. Don't feel like drawing a whole new coordinate grid. All right. So since the next one's vertex form, I don't really need a table. We can still use one if we want to, but this next one is honestly should be easier. It's set up well for graphing. So vertex form, my h value is 4, my k value is -1. So that means my vertex is 4, -1. This means right 4, this means down 1. Could still use a table of values. Vertex form is just faster this way. Much faster, actually. So there's my vertex. And then the A value is -1/2, which means it's going to shrink and reflect. So it's going to go downwards instead of upwards, and it's going to be flattened. So if my middle number is -1, 4, still might help to make a little XY table. Just to organize our work. My parent function, what the heck am I doing here? 41014. And then my pattern is going to be -1/2 of that. So -2, -1/2, 0, -1/2, -2. So negative means I go down. 4 minus 1/2. Oh gosh, I did that so wrong. Put my x's where my y's should be, and my y's where my x's should be. This should be 4. This should be -1. Okay, so -1 minus 1/2 should be -1/2 on both sides. and then down another 1.5. I should end up at -3. Another way to do this with the fractions, if you don't like them, again, you can always plug in your numbers. Or to get from 0 to -2 is -2. So to get from 4 to 6 should also be -2 in the table. It's just patterns, just ways to use the stretch that make you avoid having to plug in so many digits. So -2, -1.5 is like right there. 5, -1.5. 2, -3. It's like right here. 6, -3 is a little bit off the edge this way, but we can manage. So it's much shallower, much flatter than the last one was. Had a lot more examples of these in the YouTube videos, so it might be worth going back and taking a look at those old notes keys to see how we did it and get familiar with it. You can always fall back on plugging your numbers in, though. Number 29 gives us a formula for a firework. It's supposed to explode at its highest point. So the equation up here, h is height, t is time. Okay, so what we have to ask ourselves is what formula is most appropriate here. The quadratic formula, if we're looking at a projectile, the quadratic formula gets us the launch point and the landing point, but that's not what we want. We want its highest point when it explodes. So the firework never actually comes back down this way. So this is going to be the vertex. All right. We want to find the x part of the vertex first, which is our axis of symmetry, -b/2a. So that's the thinking here, is which spot are we looking for? So -b/2a is -85 over 2 times -16, -85 over -32, and quick grab out a calculator, because that's going to be some sort of decimal. We'll round to 2.66. If we're off by 100th or something at the end, I'm not going to be too upset here. So letter B, that answer is when, by the way, 2.66 seconds. Letter B is how high. To figure that out, we have to plug our time back in, and that gets us the y value of the vertex. So we want to know height when we plug in 2.66 for t. All right, so let's figure that out. It's going to have decimals. That's fine. We'll just keep rounding to 2 decimal places. We're not in a physics class right now where we might care about being a little more accurate. So this term is -113.21 plus 226.1 and I get 112.89 feet. All right. So there's that. Again, just have to choose what point are we looking for in its flight. Now we're simplifying radicals. So now we're into chapter 9 stuff. All right. So we're going to handle this whole problem with the mindset like we have to get this radical out of the denominator. It'd be nice if that was a perfect square because it'd make our job easier. But what I'm going to do to start here is times square root of 3 over square root of 3. Okay, it's kind of like when we're trying to find common denominators, but we're doing it for a different reason now. We're doing it because we know square root of 3 times square root of 3 becomes square root of 9. Square root of 9 is just 3. So when I multiply two of the same square root by each other, the square root's basically just gone. So the top becomes square root of 150 r to the 5th. The bottom just becomes 3. It's the first step in our process. Now I want to simplify the top. So I'm going to do, just pull the top out and do it separate from the bottom. 150, we're going to look for pairs of factors. Okay. The other way to do this is to look for a perfect square in the problem, in the factor. So I might keep a list of perfect squares on the board just to remind us what those are. But we're looking for things in groups of 2. So with the r as well, we can make r squared, and r to the first power. 2 groups of 2 and a group of 1 make up our original 5. All right, so here we have square root of 3, square root of 2, square root of 5 squared, because I found 2 5s, square root of r squared, square root of r squared, and square root of r. Anything that has the exponent and the square root, those cancel out. So that's just a 5, that's just an r, that's just an r. Those guys get to come out to party. So now outside stuff stays together, inside stuff stays together. I get 5r squared times the square root of 3 times 2 is 6, r, over 3 back from the original part of the problem. All right. This is honestly a little bit of a longer one. They won't all take this many steps, but this one made us simplify the denominator, then simplify the numerator. Sometimes we'll only have to do 1 or 2. Number 31 is going to make us use the conjugate. The conjugate was when you have an irrational denominator, we can multiply by basically one of the 2. 5 or square root of 3 has to become opposite, has to get a negative. So multiply the numerator and denominator by the conjugate. And this will get us a new denominator that isn't irrational anymore. So we've got to multiply 5 square root of 3, 5 plus square root of 3 by 5 minus square root of 3. This Punnett square is going to be our best way to multiply this. 5 times 5 is 25. 5 times square root of 3 is just 5 square root of 3. 5 times negative square root of 3 is negative 5 square root of 3. Negative square root of 3 times square root of 3 is going to be negative square root of 9 if you want to think about it that way. But again, just like last problem, multiplying a square root by itself just gets rid of the square root, just like the square root of 9 is 3. So we don't really need to think about it like the square root of 9, but if that's how your brain likes to work right now, that's perfectly fine. So these two are opposites. They're like terms because they have the same radical part, square root of 3, but negative 5 and positive 5, it's going to make 0 square root of 3. And we all know 0 times anything is 0. So what this boils down to is 25 minus 3. So our new denominator is 22. That was the whole point of this, was to get a rational denominator. So that's our new denominator, 22. Goes right up there. And then these, on the top, multiply by 3, because to multiply fractions, we just multiply straight across. 3 times 5 is 15, minus 3 times square root of 3 is just 3 square root of 3. So that's using the conjugate to rationalize the denominator. We don't want square roots down there, so that's our way of getting rid of a square root when we have addition or subtraction like this. There's this thing called the conjugate. All right. Next up is simplifying one where we have to combine like terms. So here we're going to want to simplify all these radical parts. So this one's going to come out to 25 and 11. So root 25 and root 11. And then still with that root x and the 3 in front. So we're going to do each whole term. want to write it this way so I don't lose track of anything. All right, then 10 root 23 and root x, neither of those can simplify. 23 is a prime number. Minus 3. Then again, 11 is a prime number already, so that one can't be simplified either. So the only one that really changes is this first term, because I was able to factor out a 25. Square root of 25 is 5. So that's what it kind of looks like. Then outside, outside, inside, inside is how we multiply. 3 times 5 is 15. And then 11 and x make 11x when we put it back together. This doesn't really change because nothing's simplified. So I'll just put the 23 and the x back together. Same thing over here. Just put the 11 and the x back together. Now that everything's simplified, we can look for like terms. Like terms are going to have matching radical parts. So these both have square root 11x. They have matching radical parts. So I'm going to do 15 minus 3. That's 12 root 11x plus 10 root 23x. We also have to respect variables. The plan isn't to throw any curveballs at you, but if I had like an x out front here, that would also make a difference, but luckily not a big issue for us right now. So that's all we got to do for that one, is we have to simplify all the terms and then see which ones are like terms and add them together. One final one is going to make us distribute. So when I distribute the square root of 3, each term gets multiplied by it, and I multiply it by the stuff under the radical because it's under the radical. So I end up with 2 square root of 15, 3 times 5 is 15, minus square root of, let's see, this is going to be 441. Check my math there real quick. Yeah, that sounds right. So now we would try to break these things down. 15 doesn't have any perfect square factors, so this one's good. First one's all set to go already. The second one, 441, actually is a perfect square already. Square root of 441 is just 21. All right, so we might have to combine like terms there, but not for this problem. All right, last problem on the review. This one's graphing a square root function. So the first thing we're actually going to want to do here is find the domain. Remember, we're not allowed to square root a negative, so I take whatever's under the square root symbol and make sure it's greater than or equal to 0. So that's what I start with. Negative x minus 1 is greater than or equal to 0. Once we solve this, not only does it give us the starting location for our graph, it answers the domain question. So let's solve for x, plus 1 and plus 1. Negative x greater than or equal to 1. Divide by negative 1. That's important not to forget to flip the symbol here. We divided by a negative, so that makes us flip the inequality symbol. So flip. And we end up with x less than or equal to negative 1. So that's domain. Draw a squiggly there so it's obvious it's not range. So we start with negative 1, and then we work our way down because we're supposed to be x less than or equal to negative 1. All right. Now what's really best is to go up by perfect squares. So this is kind of like my 0. Then I want to do 1, and then 4. So negative 5 is going to be better here. And then I'm going to want to go by another 5. So negative 10. All right, I'm choosing these numbers specifically because they're going to make perfect squares for me. You can just go in order. You're just going to get uglier decimals. That's where we got like our 1.4 and our 1.7 and stuff. But this is just, if you work your way up by things that are going to be perfect squares, you'll get prettier looking numbers. So now I got to plug these in. If I plug negative 1 in for x, negative 1 is 1. 1 minus 1 is 0. Square root of 0 is 0. So negative 1 comma 0 is my first point. That actually tells us what the range is going to be already. 0 is going to be my lowest y value because it's only going to go up from there. So y greater than or equal to 0. We'll see that when we're done graphing too. If I plug negative 2 in, negative 2 is positive 2. 2 minus 1 is 1. Square root of 1 is 1. So negative 2 comma 1. Plug in negative 5. Negative 5 is 5. 5 minus 1 is 4. Square root of 4 is 2. 1, 2, 3, 4, 5, up 2. And then negative 10. Negative 10 is positive 10. 10 minus 1 is 9. Square root of 9 is 3. So negative 10 comma 1, 2, 3. That's going to make this sideways parabola looking thing, just like it did during the unit. All right. So now when we compare this, the parent function was normal y equals square root of x. Ours starts left 1 and it's reflected over the y-axis. There's other things too. It can be stretched or shrinked both vertically and horizontally. It can be shifted up or down. You can really tell by looking at your graph once you're done. All right, that's the whole practice exam. Make sure you come with any questions you have for whatever review sessions we have left before the exam.